Hello, I am Madhuchanda Brahma, a PhD student in Nanoscale Device Research Laboratory in ISC Bangalore. In this video, I am going to discuss about a recent publication on Germanane MOSFET for Subdeca Nanometer High Performance Technology Nodes, and this has been published in IEEE Transactions on Electron Devices. So now we are going directly into the topic. First, a brief about the background and motivation of our work. Now, we are all aware that over the past few years, there has been extensive research on atomically thin two-dimensional materials as an alternative channel material for transistors going beyond the Moore's law. Most of these materials like graphene, HBN, phosphorin, transition metal dichalcogenants like MOS2, WS2, etc. All these are naturally available in layered form, where two-dimensional platelets are weakly bonded by the van der Waals forces, but efforts are not limited only to this. It has been extended to extract 2D analogs from conventional bulk materials also like silicon, germanium and gallium nitride. And among these materials, germanane, which is a hydrogenated monolayer of germanium, has gained much attention. Now the stable structure of germanium has already been reported for the first time in 2013 by this group of Elizabeth Bianco, and then it has been used for fabrication of Schottky diodes and even FETs by this group who published their paper in 2D materials. Now, what is the specialty of this material? Unlike the TMDs, which show higher band gap and higher effective mass, germanium inherits a very interesting property of low effective mass with a relatively higher band gap. Now, high performance switching devices demand channel materials with low effective mass in order to have very high on current. So, germanium stands a very good chance in this respect, and this thing only motivated us to exploit this interesting characteristic of germanium to assess if MOSFETs with channel lengths less than 10 nanometer are able to meet the ITRS 2028 high performance projections. Now first we'll start with the device structure and the Hamiltonian we formulated. This left hand figure shows the sketch of the simulated device cross section. LCH is the channel length which is exactly equal to the gate length which is LG, and the three different values of LCH have been taken for simulation, which are 7 nanometer, 5 nanometer and 3 nanometer. The effective oxide thickness is set to 0.47 nanometer and the supply bias is taken as 0.6 volt. Now you see the source and drain extensions are LS and ND, and these are uniformly doped either N type or P type, and their length are set to 30 nanometer so that the charge neutrality conditions are achieved at the contacts. The offset current for all the devices have been set at 100 nanoampere per micrometer. Next, the first principle based calculations on germanium has already been reported in a previous publication from our group by R.K. Ghosh et al. According to this paper, chair morphology of germanium has better potential for transistor application than its boat morphology. And this is a reason we perform all our calculations on germanium chair structure. Now, monolayer germanium in the chair configuration has isotropic conduction band and valence band. So, what we did for the MOSFET is that we chose a single band effective mass Hamiltonian, and for the P MOSFETs, since this material has two valence bands, light hole and heavy hole, so we developed a two band K dot P Hamiltonian based on its analogous graphene counterpart. And in this Hamiltonian you can see we have this K which is Kx, Ky, and this is actually the in-plane wave vector, and the Ml and Mh are actually the light hole and heavy hole effective masses. Now what we do is we tune the values of Ml and Mh, and by doing that we find the matching between the K dot P band structure and the DFT predictions, and we found that this matching is quite good in a window of almost 0.3 EV, which is close to the valence band maxima at the gamma point of the Brillouin zone. And the C parameter in the figure you see is actually the lattice constant. Now next I'll discuss about the methodology we followed for modeling the transport in this device. What we do is we do self-consistent solution of transport equations under the non-equilibrium Green's function formalism with the Poisson's equation. Now the steps are clearly shown in this flow chart. We start with a guess potential and the Hamiltonian that we generated as discussed in the previous slide, and then we start solving the transport equations. From the transport equations we get the electron and hole density, which we feed into the Poisson solver to calculate the final potential. If the difference between this guess potential and the final potential is less than the tolerance value, then the loop converges and we calculate the final current and charge densities. Now we briefly discuss the equations without going into too much details. If you want to know about it more, then you can refer our paper. We assume the device is translation invariant in the y direction, and this actually helped us to parameterize the Hamiltonian and the Green's function in terms of the transversal wave vector ky. And for each wave vector ky, the retarded Green's function is calculated, and this sigma s and sigma d are the self energy matrices associated to the source and drain contacts. Now from the retarded Green's function you can see that we calculate the electron and hole Green functions, which are denoted as Gn and Gp, and the carrier densities are calculated from the diagonal elements of Gn and Gp. And you see it is denoted by Ni because we calculate it from the diagonal elements, and Gnii and Gpii are actually the on diagonal elements of the electron and hole Green functions. But the current density is calculated by the off diagonal elements of the corresponding Green's functions and the Hamiltonian. Now we want to mention one point, that we use the recursive Green's function algorithm to calculate this carrier and current densities, and the details of this will be found in our paper. And after solving these transport equations, what we did is we feed these things into the 2D Poisson solver, and the 2D Poisson's equation is solved in the cross section of xz plane by making use of the Gauss law, which you can see in the slide. And the discretization of this Poisson equation is entirely based on finite difference method, for which we enforce Dirichlet boundary conditions on the metal gate electrodes and Newman boundary conditions on the rest of the edges. Now for our study, we had assumed ballistic transport, and in order to validate this approximation, we have estimated the phonon limited mean free path of both electrons and holes, and found out that they largely exceed the channel lengths considered in our work, and thereby it is suggested that for these devices the carrier phonon interaction is very negligible, and you can find the details of this entire calculation in our paper. Next I'll present the results we have obtained. First I'll present the static performance matrix that we obtained from our simulations. We see that Germanane based devices with channel length scaled to very small dimensions of 3 nanometer still appear to be able to provide an on current which is comparable to the ITRS projected value, and this is indeed remarkable. And from this table and also the transfer characteristics figure which is shown below, we see that the on current is gradually decreasing as we scale down the channel length from 7 to 3 nanometer. Now a bit about this figure, I want to tell that this figure shows the transfer characteristics and as well as the percentage of tunneling current marked on the right hand side. The vertical blue line actually indicates the gate voltage at which this percentage of tunneling current in P MOSFET is 50%, and the red dotted line represents the slope at Vg equal to 0 volt of the transfer characteristics of the N MOSFET with channel length having 7 nanometer. Now the reason for this gradual decrease of ion with the scaling of channel length is due to the concomitant increase of the source to drain tunneling, and due to the enhancement of the tunneling, shorter devices require a higher barrier in the off state so that they have the same I-off as devices with longer channels. But unfortunately, a higher barrier in the off state directly entails a higher barrier in the on state, hence resulting in degradation of the on current. Now the enhancement of tunneling for decreasing the channel length also results in the degradation of the slope of the transfer characteristics at low Vg, which further contributes to the ion reduction. This you can see if you observe the red marked lines of the three figures. Now this figure not only allows us to compare this decrease of ion, but also it helps us to compare the behavior of N and P MOSFETs as a function of VG and LCH. You see, I have marked yellow and brown circles. The yellow circle represents to the low VG regime. And here we see that the PMOS current is always less than the NMOS current, and the situation worsens for smaller channel lengths like 3 nanometer. And the brown marked region is the high VG region. And in this region, the PMOS current gets closer to the NMOS current and even exceeds it in case of higher channel length like 7 nanometer. In the next slide, we'll explain the reason behind this phenomena. So for this, what we have done, we have plotted the current spectrum plots superimposed on the subband profiles of both PMOS and NMOS. First, we focus on the low VG regime. The slope of the transfer characteristics is found to be always higher in case of N MOSFETs. To explain this, we see the figures, and I want to mention that all these figures have been obtained at a VG of 0.4 and 0.6 volt, which is actually in the moderate high regime. Now in P MOSFETs, the density of states is higher because we have seen that it has two bands in the valence band, which is the heavy hole band and the light hole band. And due to this reason, there is a very small distance of the source Fermi level EFS from the valence band edge in the P devices. You can see this clearly in the figure, and the difference between the source Fermi level and the conduction band in N devices is quite high than the PMOS. Therefore, in P MOSFET, what happens is the carriers are injected very close to the base of the channel barrier, and therefore it is forced to tunnel. On the contrary, in N MOSFETs, EFS is far enough from the conduction band edge to allow a substantially higher thermionic component to flow even in the low VG regime. And this higher tunneling in the P MOSFET finally degrades the electrostatic control of the current, and it results in a lower slope, as you can see in the lower VG regime of each of the three curves. And when the channel length increases to 7 nanometer, there is a reduction of the relative importance of the tunneling. And so the difference between the NMOS and PMOS transfer characteristics in the low VG regime diminishes for higher channel length like 7 nanometer. Next, we focus on the high VG regime, when the percentage contribution of the thermionic current exceeds that of the tunneling current. We see that as the percentage of tunneling current decreases below 50%, the current in PMOS starts rising faster than in NMOS. The approximate VG value, let us say this, it is V50, at which this effect starts arising. And this V50 value depends on the channel length, because you see that as channel length decreases, this V50 value shifts more towards the right of the VG scale. The channel barrier allows the light holes to tunnel, while blocking the heavy holes due to bigger effective mass. The heavy holes are main contribution to the transport by sustaining the thermionic current, and this starts to play a very significant role when the channel barrier is low enough, that is when the VG is high. In this both figures of the spectrum plots, we see that we have already reached this region of moderate VG. For 7 nanometer, you can see that we have already crossed over the V50 region, and most of the current in both PMOS and NMOS is now over the barrier. Whereas in this lower channel length like 3 nanometer, the V50 value has not yet been reached at VG equal to 4 volt, and so the current is mainly tunneling. Now for a given VG, the longer devices exhibit a smaller barrier with respect to the shorter ones, and this is the reason that the V50 value shifts more to the left in case of higher channel lengths, and the P MOSFET current therefore starts overtaking the N MOSFET current much before than the lower channel length devices. Next, we discuss about the dynamic performance metrics of the devices. These are very useful because it helps us to predict how the devices will behave as switching elements. For this, we calculate these three parameters, which is the intrinsic switching delay tau, the gate capacitance CG, and power delay product PDP. And all these values are listed in the table in front of you. The equations are also shown above. And we have also plotted the variation of CG as a function of VG for different channel lengths. From this figure, you can see that there is a sudden increase of CG in P MOSFETs for higher VG. The reason lies in the quantum capacitance which is proportional to the density of states, which is actually very high on P MOSFETs. But this effect is very less, you can see, in N MOSFETs, because here the quantum capacitance is limited by the lower density of states of the low effect mass N MOSFETs. Now for both N and P MOSFETs, the values of tau and PDP are substantially lower than the ITRS requirements, as you can see in the table, and this is desirable. However, tau increases as LCH is scaled down, but PDP decreases. This behavior of PDP is due to the decrease of the value of CG, which is nothing but a manifestation of the reduction of the Q on minus Q off. And the increase of tau actually reflects the strong enhancement of the tunneling for shorter length devices, which entails that the ion decreases faster than the Q on minus Q off when LCH is scaled down. Now, finally, what we do is we compare this energy efficiency and the switching capability of Germanane monolayer MOSFETs with respect to other 2D material based MOSFETs, which are marked in these two figures, and these devices are monolayer black phosphorus MOSFETs in both armchair and zigzag directions, MOS2 MOSFETs for two different channel lengths, and also conventional CMOS high performance devices, germanium high performance devices, and 3-5 high performance devices. And we see in both the figures that Germanane MOSFETs can largely meet the ITRS HP performance, and even it outperforms the 3-5 and the germanium high performance FET requirements. In the energy delay plot, the points referring to the most performant devices, that is Germanane N MOSFETs, the black phosphorus MOSFETs, and the MOS2 MOSFET with the shorter channel, gather around a equi-PDP line, which means that the switching speed can be increased at the expense of a higher energy consumption. And we see that among all the devices, only the armchair black phosphorus MOSFET exhibits smallest intrinsic switching delay, and the Germanane N MOSFET with the channel length of 3 nanometer exhibits the lowest switching energy. Next, we move on to the delay versus ion I-off plot, and this shows that Germanane N and P MOSFETs with LCH 7 nanometer, the MOS2 MOSFETs, and the zigzag black phosphorus MOSFET, all these belong to a very restricted region of the plane, with only the armchair black phosphorus MOSFET outperforming all these devices. So what we can summarize is that our self-consistent full quantum simulations for determining the potentiality of this sub 10 nanometer Germanane MOSFETs against the ITRS 2028 projections for high performance devices proved to be quite successful, because we found that both the N MOSFET and P MOSFET offer excellent ion and very large ion I-off ratios even when they are scaled down to a very small channel length of 3 nanometer, and this is far beyond the ITRS projected limits. The values obtained for the dynamic figures of merit, such as the intrinsic switching delay, the power delay product, also indicate that our MOSFETs can meet the ITRS projections and compete with other 2D material based MOSFETs. So in all, we can say that Germanane MOSFETs represent a very viable option for high performance ultra scale device applications in the future. So thank you for paying attention to this discussion.